So we're going to have a look at a simple harmonic motion question here that concerns a pendulum. So this pendulum, there's two pendulums actually. So one of them is on the surface of the earth and the other one is at an unknown height. That's going to make the period of the second pendulum be 2% more than the period of the first pendulum. So whenever I see a question about pendulums, it will be fairly wise to start thinking about the formula that's specifically for pendulums, because it has one formula that can only be used for pendulum questions. We also know that we pretty much haven't been given any other details apart from this 2%. So very likely we're going to have to look for a ratio or look for ways around filling in all of the other values. So we might be trying to cross cancel them if we let one equation equal to another equation. So the first thing I'm going to do is just write out that equation for the period of a pendulum. Again, this applies only to pendulums, so that if you see a question on a pendulum specifically, there's a very good chance you'll have to use this formula. The way they've got it done in the actual mark scheme is the way I'm going to do it first, but I can show an alternate method afterwards. So the way they do it in the mark scheme, what they're looking for you to do is base period, your based off period, you know 2 and pi, they're constants, but you don't know the length. So you want to find out the relationship between period and g, so you can discard everything else. I know that once we get g, we still need to figure out a height. So if I'm figuring out the length between period and acceleration due to gravity, it's very unlikely I'm going to be able to use that to get a height unless I can link it into a second formula. So a formula that links acceleration due to gravity to height is this one here, but it's the height from the Earth's surface, from the center of the Earth. Now, if we look down below the question, they already talk about the radius of the Earth, which would be this value here. So there's a very good chance that using this formula in conjunction with this formula is going to work out for us. So if I want to make these two formulae equal, figure out the relationship between period and height above the Earth's surface, the link between them is going to be g. So if I can I've already got g figured out here. It's the subject of the formula. If I can make g the subject of this formula, then I can just let these two equations equal to each other. So my first step is going to be to make g the subject of this formula. So I'm going to write out the formula as it is. I'm going to try and work to make g the subject of the formula. So I'm going to get rid of 2 pi off of this side by dividing both sides by 2 pi. I know I want to split up this fraction, so I'm going to split it up first of all by splitting it up into root L over root g, which is the same as the square root of both of them. Cross multiply now, so I get period times the root g equals 2 pi root L. Then I want to get rid of t to make g the subject of the formula still, so I divide both sides by t. Now to make g the subject of the formula, I just square both sides. If I wanted to, I could square this here now, but I'm holding off on doing that just because it's going to make my life a little bit easier later. So now that I know that this is equal to g and this is equal to g, I can equate these to each other because both of them have the same value. Now, I want to figure out, my goal is to figure out the relationship between period t and the distance from the center of the Earth. So I'm really just trying to see what the relationship is between them. Is it proportional? Is it inversely proportional or anything like that? So to do that, the first step is going to be to get rid of the square root sign. So what I'm going to do is get the square root of both sides. If I get the square root of the left hand side, the square root of the right hand side, the square root and square will cancel out on the left hand side. So I'm just left with what's inside the brackets. And on the right hand side, the square root and square will cancel out on the bottom to just leave me with or on the bottom, or the distance from the center of the Earth. At this point, I can kind of ignore everything else. I've got the relationship between period and distance from the center of the Earth down. I can see that it's directly proportional. So at this point, I know that that's the relationship between them. So I can use that to create a ratio. So if period changes, the distance from the center of the Earth will change proportionately. So the new period divided by the old period is going to give me the new distance from the center of the Earth divided by the old distance from the center of the Earth. The new period is 102% of the original period, so I can put 102 over 100 or 1.02 over 1, it doesn't matter. The ratio is still the same. That ratio will equal the new distance from the center of the Earth divided by the old distance from the center of the Earth, which is 6371. I put in kilometers here because I'm not using the standard units. If you wanted to put it in meters, that's fine. The reason why I'm able to shortcut this is because there's no other units in the question. It's just a ratio. So if I get the answer right, well, that's fine as long as I remember that the answer is in kilometers. We're on to the home stretch now, so the last thing we have to do is cross multiply both of these terms. So we get 1 multiplied by the new distance from the center of the Earth is equal to the product of the other two numbers, which are just constants. Multiply these out, and we get the new distance from the center of the Earth is 6498.42, which we know is in kilometers, and it's important to remember. We take away what the radius of the Earth is, which is 6371 kilometers. So to visualize this, if this is the center of the Earth, this is where the old pendulum was, this is where the new pendulum was. And if this is R2, and this is R1, well, our height here is going to be the difference between those two. So once we found the difference, that's 127.42 kilometers. So if you're not comfortable with the ratio type of questions, I'm going to show you an alternate solution now that will do just as well for you. It might take a little bit longer, but it should be roughly comparable time-wise. The reason I went through this one first, I actually think it's kind of more complicated to understand, but it is the one that was on the mark scheme, so I guess they are expecting that standard. So in the alternate solution, we have our period is equal to 2 pi times the root of L over G. And this is pretty similar to the last one. When you see a pendulum, very good idea to write out the pendulum formula. I know that the new period, or the second period, is 102% of the old one. So I just wrote that as a decimal to save a little bit of space. So T2 is equal to 1.02 times the original period. Now I've written out 2 pi times L over G times the root of L over root over G for each of them. But I've written out 1.02 before the original one because this period is going to be 1.02 times the old period. I made sure that the G was differentiated as G2 and G1. The new G, new acceleration due to gravity, the old acceleration due to gravity. But we're assuming that the length is going to stay the same throughout, and 2 pi is always going to be equal to 2 pi. So at this point, like I said, a good strategy, because we don't know L, is to seek to cancel things out from both sides. So 2 pi is on both sides, we can cancel that out, and the root of L is on both sides, we can cancel that out. This leaves us with 1 over the root of G2 is equal to 1.02 times 1 over the root of G1. We can write this right inside as just putting 1.02 over the root of G1. So at this point, what I want to do is find out the relationship between the two G's. It would be easier for me to do this if I could get rid of the square root sign. So I'm going to square both sides. If I square the left hand side, I get 1.04 times G2 is equal to G1 on the right hand side. I know I need to use this information about the relationship between the G's to get me something to do with the change in height. So I'm going to go back to the other formula that we have, which relates acceleration due to gravity to the distance from the center of the Earth. So for G2, I write it out as big GM over R2 squared. And for G1, I'm writing it out as big GM over R1 squared. Obviously, as before, G2 is 1.04 times bigger than G1. I could fill in G, the universal gravitational constant, or big G. I'm not actually given the mass of the Earth in the question, so I couldn't actually fill that one out. But because both of them are a similar term or a common term on both sides, I can just cross them out for each side. So that gives me 1.04 over R2 squared is equal to 1 over R1 squared. So here's where a little bit of extra calculation comes in. You cross multiply them to get this first line. And then we want to get what R2 is by itself, so we get the square root of both sides. This brings our 1.04 back to being 1.02 because we previously squared that. So we end up getting R2, the new distance from the center of the Earth, is equal to 1.02 times the old distance from the center of the Earth. R2, when we fill it in, is equal to 1.02 times this distance. I've actually put it in meters this time. So that gives us the distance from the center of the Earth as 649,820 meters. As before, once we've found our distance from the center of the Earth, we want to take away the radius of the Earth, and that will give us a height. This time, again, the height is in meters because I worked it out in meters throughout the question. For the velocity time graph for the oscillating spring, it's important, I guess, to realize that your velocity is going to be changing direction, because at some points it'll be above the point of equilibrium and it'll be accelerating downwards, and at other points it's going to be below the point of equilibrium and it's going to be accelerating upwards. So the spring is going to start off below the point of equilibrium, they say in the question, and it's going to accelerate upwards. Generally, when something is moving upwards in terms of up-down movement, we say upwards is negative and downwards is positive. This is just because gravity acts downwards, so most things end up coming downwards eventually. It's just convention, you're not going to gain or lose marks for that. So this thing is going to start off with no velocity as it's released, then it's going to accelerate or get a greater velocity. It's going to be doing that in the negative direction. So we can start the velocity off here as having no velocity, then it's going to accelerate and pick up velocity in the negative direction. As it passes the center, it's going to have the highest velocity because its velocity is about to change and start accelerating in the opposite direction. So as it goes past this, towards the other side, towards being above the point of equilibrium, it's going to start to accelerate in the opposite direction, moving back towards having zero velocity. Its point of zero velocity will be when it's reached the furthest up it can go and it's getting ready to start moving in the opposite direction again. Now it's going to start moving downwards, so its velocity will be positive. And this shape will just repeat itself.